In this video, we are going to talk about designing boards with very high current power supplies. And by very high current, I mean power supplies that can deliver hundreds of amps or even over thousands of amperes. I'm not an expert for this topic, so I had a call with Steve. I recorded this call, and that's what you will see in this video. I really hope you will find it interesting and useful. Here is my call with Steve. We are going to talk about high current power supplies. And when we say like high current power supplies, what does it mean? What kind of current we are talking about?
So 500 amps is probably where it starts. And there are plenty of Intel processors now that are at 500 amps or above. And there are a lot of GPUs that are well above that. So current state of the art is probably in the range of about 1,000 amps. There are a few companies that are doing 100 millimeter ASICs that are in the 1,500 amp to 2,000 amp range. But I would say the current state of the art, we could probably consider that to be around 1,000 amps.
Wow. And what kind of voltage we are talking about?
Most of these are around 0.7,
0.7.
0.7 volts.
Mm-hmm. Are there also some for like higher voltages or?
I haven't seen any higher voltages. There are some at 0.6. They are, trying to drive that down, but the noise margins get kind of small. So right now, most of them are still in the range of 0.7.
Mm-hmm. Okay. So if someone would like to design this kind of power supply for high currents, what they need to be careful about? Do they need to care about like copper thickness or what is important?
There are a few things that are important, but one thing is that it's really important to minimize the inductance between the power supply and the ASIC, because that's going to result in the number of decoupling capacitors that you need. And so first is how close can we get the power supplies to the ASIC? That's probably the first consideration. There's probably also the second and third consideration. Once you get through getting the power supply to be as low inductance as possible and as close to the chip as possible, then after that, then you can start to look at other effects. One of them maybe is thermal, although I think thermal is not really the biggest issue with the power supply itself, because if you think about it, the power supply is 98% efficient, on that order in most cases, well into the 90% range. So a kilowatt, you're going to dissipate maybe 50 watts or 20 watts into the power planes. But you have 1,000 watts dissipated in the ASIC that also has really good copper connections from the balls into the power planes.
Oh, so basically the heat will flow from the chip to will rather flow from the chip to the power supply than from power supply somewhere else.
Exactly. So, I mean, they all add together, but I think you're getting a lot more heat from the ASIC into the board than you are from the power supply into the board. So that's kind of the lesser problem. And of course, the heat goes the other way too. So the heat that's dissipated in the VRM gets sucked up through the balls of the ASIC also, right? And goes out through the cooling system that's sitting on top of the ASIC. So it kind of goes in all directions. Some of these boards, the boards themselves are water cooled. The devices on the boards are water cooled, but not too many of them. I mean, we're just starting to see that. Now, Vicor was looking at the possibility of building on-package VRMs. In fact, they did it, right? They actually do offer on-package VRMs, and that goal is really just to keep going along the thought that says that we need to get the VRMs as close to the ASIC as possible to minimize the inductance.
So basically, you don't you don't design this kind of power supply by yourself. You place a module on the board close to the chip, and that's how you generate it. And,
correct.
And when you say it like water cooled, so you say water cooled boards or PCBs or water cooled heat sinks, or what do you mean?
Both. In fact, at Picotest, we're actually working on water cooled printed circuit boards now, very small ones for our probes. because we do have very high heat concentrations actually in probe heads. And how do you get the heat out of that? The only way we can get the heat out of a tiny little probe like that is liquid cooling. So you'll see actually Picotest is going to come out soon with water cooled printed circuit boards.
So the water flows inside of the PCB?
Yeah, we're actually running two parallel paths right now. One is to have water channels embedded in the heavy copper inside the circuit board. And another one is to bring copper coins through the printed circuit board to a backside manifold. And which way is going to turn out to be, optimum from a cost performance standpoint, I'm not exactly sure, but we are actually looking at both of those options. And when you get to these high power systems, that becomes really important too, is how do you get the heat out? And mostly it's going to be water cooling.
So is it like normal water or it's like some kind of special water or?
Um, I mean, there's liquids in it. Think of it more like an antifreeze, right?
Mm-hmm.
So there are chemicals in it, but it's a liquid cooling system,
Mm-hmm.
and
So it's not
um,
like it's not going to like cause corrosion, for example, or
no, because the water itself is isolated
mm-hmm.
inside the channel. But right now, a lot of computer boards are water cooled. The ASIC itself, it's pretty common to have water cooling systems for those.
Yeah.
And they circulate water and they have a radiator, in the front. And then they got big cooling fans that blow through the radiator. So that's kind of common.
That's what
Uh,
I thought, but I never really knew that you can flow water inside of PCB.
well, yeah, eventually you have to. And what is it they say? Necessity is the mother of invention, right? So you do what you have to do. Of course, Intel is looking at other directions too. Intel is looking at actually putting the power supply onto the ASIC. And if you put the power supply onto the ASIC, well, that's about as close as you can get, right?
So you would
Um,
power up chips like, I don't know, with 12 volts, for example.
yeah,
Wow.
exactly.
Okay. Uh,
Um, whether that's ideal or not, I don't know. I mean, at 1,000 amps, even 12 volts is almost 100 amps, right? So it's still an awful lot of current that you got to move around, and now you're moving that around on the package. It could be more beneficial to get the voltage up, which is why you're seeing 48 volts now in a lot of these high power applications. It's to get that current down, and also since the power supply input is a negative resistance, and that's a term that people struggle with. But think about it: if a switching power supply has a constant output power and high efficiency, then the input power is constant also. And that says that if I raise the voltage and I have the same power, the current had to go down. And if I have a current that goes down when voltage goes up, it's a resistor, but it's negative. And that becomes really important because negative resistance is actually the core of an oscillator.
mhm.
And that's something that people have studied it for a long time. In fact, it's probably one of the most researched doctoral thesis topics is the Middlebrook criteria negative resistance oscillation. So inductance on the input side of the switching converter will tend to oscillate as a function of the negative resistance. And negative resistance is a function of the voltage squared. So as the voltage goes down, the negative resistance goes down at a second order rate. So it's declining very quickly. So it becomes really advantageous to raise the intermediate voltage from 12 volts to 48 volts for that reason.
I would
Now
like
that's
to
a
ask,
problem.
yeah, I would like to ask, you mentioned the inductance is important because it can lower number of decoupling capacitors, correct?
Yes. On the output side, yes.
Okay, so can we talk a little bit about this? Because maybe, many people
Sure.
just think like you connect the output from the power supply to the chip, and now they will be thinking like why this should influence number of capacitors.
Right. So, I mean, when you get down to it, the only reason that we have capacitors is to cancel inductors. If we didn't have inductors, we wouldn't need capacitors. Um, and inductance comes from different places. First, it comes from the VRM, and the VRM has an inductance that's associated with the output filter inductance and the switching relationships. I have lots of papers on that, but here I'm showing one of the examples for an equation of what the inductance looks like.
I have a question.
Yeah.
So why the inductance is wrong? What is it going to cause?
So if the inductance is too high, it's going to cause a lot more capacitors,
But
many more.
okay,
So
why? Because the power is going to be delivered kind of slowly, or
because in order to get impedance to be flat, what does that mean? That the impedance is flat? What it means is that the characteristic impedance of the printed circuit board is matched to the impedance of the plane. So what does that mean? If it was a 50 ohm cable, for example, a 50 ohm cable means that the square root of L over C, the inductance of the cable, and the capacitance of the cable, square root of L over C, is equal to 50 ohms. And the same thing is true in a power plane. So in order to make it flat, what that really means is just like in an RF network, square root of L over C divided by the target impedance has to equal 1. And if you tried that with a 50 ohm cable, you'd see that that's true.
why we would
So
like to have it flat?
Right, well, we need to have it flat because if it's not, when you get a current demand, it's going to have a much higher voltage excursion. And it's also going to result in ringing, which is going to cause EMI. So two different problems. One is the voltage excursion. The second one is the noise. So it's really important that the impedance be flat.
Oh,
And
I know, because basically, if it's flat, it means for the power supply, it is kind of just a resistance. There is no
correct.
L, there is no C. And if there is L or C, so if it's not flat, then suddenly there are some peaks, for example, and these peaks, if you are running something on your chip with this frequency where these peaks are, they can cause problems because these peaks, higher impedance, it means, for example, the not enough power can be delivered, or it can start oscillate or some reflection or something, correct?
Exactly. So if you look at the picture that I'm showing here,
Okay.
right? So you can see in the red waveform, we start out with a 25 milliohm impedance, but then it becomes inductive. And so the impedance in the red trace starts to rise.
Mm-hmm.
And then it resonates with the capacitors at about 200 kilohertz.
Mm-hmm.
And then because the capacitors have very low ESR, you can see the series resonance of the capacitor results in a really low resistance at the series resonance, and then it becomes inductive. And if you look at the blue trace is a flat impedance, pretty flat, right? So if the ASIC was able to generate noise at, say, 200 kilohertz, in the red trace, you have almost 200 milliohms, and in the blue trace, you got 25 milliohms. You're going to get 10 times as much noise in the red trace as you will in the blue trace if you can generate noise at 200 kilohertz. But then there's another problem too, because now you can see at a megahertz, the caps became series resonant, and now we have inductance leading into the chip. But the new target impedance isn't 25 milliohms anymore. Now it's only 2 milliohms. And so that raises the Q of the inductance of the package. And if we rearrange that equation to get flat impedance, C is equal to L of R squared. So in the first case, the capacitance we need is equal to the inductance of the red trace, which is 58 nanohenries, it says here, divided by 25 milliohms squared.
Is it somewhere there on the picture? Can you show by cursor?
Yeah, so this says that the excess inductance is 25 milliohms, and we can see where it starts to rise. The 3 dB point is here at 68 kilohertz. That says the inductance of this system, and that could be from the VRM, it could be from the boards, could be from the combination of the two, but the total inductance of the package is 58 nanohenries. How much capacitance does it take to fix that? C is equal to 58 nanohenries divided by 25 milliohms squared. That's how much capacitance it would take to fix that. Now, when we get to higher frequencies above a megahertz, we have this new resistance. It's not 25 milliohms anymore. Now it's 2 milliohms. So the denominator, the R squared, went from 25 milliohms squared to 2 milliohms squared. We need 100 times the capacitance now because of that impedance dip. And so it's really important that we try to keep this flat. And what that means, flat means C is equal to L over R squared. So if we have a target impedance, that's R squared, and L, that's the inductance that's seen at the ASIC. Now, what happens is the power increases at 100 watts. Maybe you have 10 milliohms for R out, and at a kilowatt, you have a tenth of that. And so that means that the capacitance went up by a factor of 10 squared. We need 100 times more capacitance because the power of the chip went up a factor of 10. And so there's this exponentially increasing demand for capacitors as a function of this inductance. And so if all else is equal, the only thing that really matters is how much inductance did we end up with at the ASIC. That's going to determine how many capacitors are required underneath it. Mm-hmm. And that becomes a huge number. You'll see that, at 1,000 amps, it's not uncommon to need more than 1,000 decoupling capacitors under the ASIC. Wow. And that's for a well-designed power plane. If you have a poorly designed power plane, you'd need a lot more than 1,000 caps. And very quickly, you'll see that just doesn't fit.
Okay. I would like to go through this one more time because this is like super interesting. And I think
sure.
It can help people to understand like how many capacitors they need and how they can maybe calculate it. So the most important equation is the C equals L divided by R squared, correct? That's the most important.
That's true. That's true.
And so we need to do this for the critical frequencies which are away from the target impedance, or?
Correct. And at 1,000 amps, the target impedance is generally 100 microohms or less.
100 microohms.
So that's typically the target impedance. I can tell you that the lowest impedance I've seen so far is 32 picohenry, 32 microohms.
Okay, so basically the R out, that's the target impedance, that would be 100 microohms for 1,000 amps.
Right.
And if it's squared, then it's like, what is it? It's 100 micro multiplied by 100 micro, correct? So that's like
yes.
What?
It's 10 to the minus eighth, right?
Okay. And so it means basically the higher the inductance is, more capacitors you will need.
Correct. Okay. So there's two things that come from this equation, and both of them people struggle with a little bit, because some people think that the goal of the PDN management is to minimize the impedance of the power rail. That's not true. The goal is to maximize the impedance of the power rail. Because if we were to minimize the impedance of the power rail, that's R out, right? So we don't want R out to be as low as it can possibly be. We want R out to be as high as we can possibly tolerate, because that's going to minimize the number of capacitors. So the question is, what is the highest R out that we can tolerate? That's where we want it to be. And then once we get through that, then now capacitance is directly proportional to the inductance of the plane. So if we can do anything to reduce the inductance of the plane, then that's a beneficial thing.
How people can get this L number?
That comes from the EM simulator, but there are some rules of thumb also.
Can you measure it? Oh, can you measure it?
You can measure it. Yes, you absolutely can measure it. And we can also simulate it in a 3D simulator. There are a lot of books that provide estimates, and the estimate of inductance of a power plane with its associated reference plane is related to the distance between the power plane and the reference plane, and the ratio of the length to the width of the plane. So the estimate would be 30 picohenries times the distance between layers.
Can you move?
Yeah, it's right. It's right here. So 30 picohenries times D per square, and square is the length divided by the width of the plane. And D is the distance between the power plane and its associated ground reference. So, for example, if we had a 4 mil dielectric, we would get 120 picohenries per square. 30 picohenries times 4 mils, that would be 120 picohenries per square. And the square is the ratio of the length to the width. So, what does that tell us? It tells us that we want to make the layers as thin as possible. And we want to make the length divided by width as small as possible. That means we want to get the VRM as close to the chip as possible. And we want the plane to be as wide as it can get.
Mm-hmm.
Now we can do things to minimize this. One is to use really thin dielectric. So at a 4 mil dielectric, we would get 120 picohenries per square. But we can go to much thinner planes than that, an 11 micrometer plane, and there is 2.5 mil FR4, and you can see at the high frequency range here, you can see how much lower inductance we get from these really thin layers.
So basically, this is why it is important to have the ground plane and power plane close to each other, because you can get very low impedance or very low inductance, and then the power is delivered more easily.
Yeah, and most of the time we'll actually interleave layers. So you'll have many power and ground layers. So it'll be power, ground, power, ground, power, ground. And that way we end up with all of these effective inductances from these planes all in parallel.
Connected in parallel. Okay.
Right. So the inductance goes down.
Lower the inductance even more.
Yeah. In reality, I think that getting below 1.5 mil dielectrics in a normal material is about as low as you'll get it. Most people probably would settle on 2 or 2.5 mils. You can use these high dielectric materials like this one from 3M. They're expensive and they're a little bit difficult to process. Not everybody can process them, but in high power computers, they are getting more common. You can see how close they have the ground and power planes together, right? 11 micrometers. And that has the benefit of adding capacitance, broadband capacitance, as well as just getting the inductance down. So when you look at the higher frequency cavity resonances, the very thin dielectrics can really help a lot with that too. There are some good papers. Heidi did a great paper on that, and so did Isvan Novak.
I would like to ask, is there any risk if you use lower and lower dielectric thickness? Like, is there a risk for a higher noise or for something else? I don't know, getting too hot and melted or short circuit, or I don't know.
I don't really know of any big disadvantages. Certainly, if you have thin dielectrics to other noise paths, they'll couple better, right? Just because they're closer together. But if you keep a power plane pair for a specific power rail, then I think that it'll do a good job of keeping external noise out. I think the biggest disadvantages are just that, number one, it's expensive, and number two, it's hard to process.
Mm-hmm. Can we go back to 2 slides back? Yeah, I would like to still talk. Yeah, number five. Why impedance is changing if inductance is still the same?
So here's the inductance of the VRM.
Mm-hmm.
And then here's the decoupling capacitors. Then the decoupling capacitors become series resonant.
And so basically, the decoupling capacitor will change the shape.
Correct.
That's what is changing the shape, not the inductance.
Correct. So what this means is that we needed, if we wanted this impedance to be flat, we needed much more capacitance. And we needed the ESR of the capacitors to be much higher, right? And that's counterintuitive because we keep making capacitors that have lower and lower ESR. There was a line of impedance controlled capacitors made by TDK, and I think they still make their ESR controlled capacitors, but they're not popular. And so most people don't use them. And they don't use them because they're expensive. And they're expensive because most people don't use them. So there's this circular reference, right? But it becomes really difficult because I think most engineers aren't really aware of how much of a problem that low ESR causes. They think lower ESR is better. And it's not. It causes terrible problems.
Because,
Because this really low impedance is the matching impedance for the next resonance, which is the package, right? So now here, the decoupling capacitors need to match 25 milliohms. Now, when I look backwards from the package, now I need to match 2 milliohms. So this isn't 25 milliohms squared in the denominator anymore. Now it's 2.
oh, I understand.
So on the package now, you need this incredible amount of capacitance because of this dip.
Because chip basically sees the power supply backwards. So for the chip,
Right.
there is this very, very low impedance, which we should meet with the decoupling capacitors, but we don't want to have so
Yeah.
many. We would like to move it up because then we can place less capacitors.
Right. And if you look, Heidi and Jack Carroll and I have done sessions at DesignCon every year since 2018. But you'll see we actually do show that. And in fact, I think in 2021 and 2022, in our papers, Heidi actually showed what happened as we moved this impedance around, looking from the die perspective. And in fact, we were able to even figure out what the optimum impedance was. And that's based on what's on the package. So one of the things that we're saying is that in the future, what we really need to know about the package is just the characteristic impedance, squared L over C.
Mm-hmm.
If Xilinx told us that our package is 2 milliohms, then we would know we have to design a power plane that's flat at 2 milliohms.
Mm-hmm.
And Xilinx could tell us what frequency they take over at. So in the example that we used in our DesignCon papers, I think that the power plane itself was only important up to about 10 megahertz. Above that, the power planes didn't do anything. It was all handled on package.
Mm-hmm.
And for that particular chip, the target impedance of the chip was at around 6 milliohms. So if Xilinx would say, hey, this chip needs 6 milliohms up to 10 megahertz, we would know exactly what to do. We wouldn't be over designing. We wouldn't be under designing. We would know exactly what to do.
This is interesting. So you don't need to care about this impedance characteristic about 10 megahertz?
Not for that package. Mm-hmm. So this is highly dependent on what's on the package. So when we look at FPGAs, some FPGAs have significant package filtering and some don't.
Okay, so when you say significant package filtering, it means all the signals about 10 megahertz in this case, or all the power noise, which is about 10 megahertz, is easily delivered to the chip from the on-chip.
Yeah, that's all handled. Yeah, it's all handled by the chip. So we don't need to worry about that. But it's different for different chips. Like if you look at a Vertex 5, there's no real package filtering. And so we're responsible to keep the noise down all the way up to the high frequencies, whereas the Vertex 7 has a lot of package filtering, and we don't need all of that. So engineers are kind of confused about what it is that they need for a particular chip. But the answer is that C is equal to L of R squared. And what we need to know is what the characteristic impedance of the package is. And if there is package filtering, we need to know what the cutoff frequency of that filter is, because that's where we can stop taking care of it, and the ASIC has it. But every stage along the way, all we really need to know is this one equation, C is equal to L of R squared. Yeah, one of the predictions I made in a webinar I gave last week on what's going to happen in oscilloscopes over the next 5 years. But one of the things that I'm saying is that the oscilloscope is going to get smart enough to do this for us. And it'll look at the plane, it'll be able to figure out what those capacitors and inductors are, and it'll tell us what the right answer is. It can even synthesize the right answer. Mm-hmm. So, for example, in a scope, we can measure impedance now, and we could get this red chart. And the scope might tell you, whoa, for that inductance, you've only got 100 microfarads, and you really needed 1,000 microfarads. And because your target impedance is 25 milliohms, the capacitor should have an ESR of 25 milliohms. And if you did that, here's what it would look like, and it can synthesize that blue trace for us. So I think that we'll start to put our artificial intelligence into the instruments because engineers have to know so many things now. There's so many things that they need to do. Not everybody's going to be a power integrity expert, uh, but the scope can dissect this for us, and the scope can tell us what this is going to do. The scope can even tell us what the transient response of that red waveform would look like.
Mm-hmm.
And so I think in 5 years, I think you'll actually see that in scopes, and they'll just tell you, hey, that's not the right cap. Here's the right cap.
I would like to ask, uh, I forgot what I wanted to ask. What I wanted to
That's
ask.
okay. It'll come back. It'll come back to you. But that's really the goal. And of course, we want to minimize the number of capacitors because every capacitor is a potential failure, and you got to pay for every one of them, and they all add weight.
I remember what I wanted to ask. When these become important? Because, many people are just designing boards without actually considering this. So when you really need to care, when you have like too many capacitors, or when you are driving currents above, I don't know, 5 or 50 amps, or I don't know when it is important.
Well, it's always important, right? The question is the sensitivity to noise. So, for example, in our online class, we showed what the power rail looks like for just a simple CMOS logic gate. It's a high-speed logic gate that we have on our board. It's a tiny little 8-cent, single gate logic device, just an inverter. We use it as a clock buffer. We actually measured the power rail noise coming from that inverter, and we measured the noise at a bandwidth of almost 2 gigahertz, about 1.5 gigahertz. So that one logic gate is generating broadband noise up to 1.5 gigahertz that goes everywhere in the board.
Because of wrong decoupling.
Yeah, for sure. And of course, it certainly affects the noise on the logic gate. So how do you decouple it? It's kind of tricky because they put the VCC in one corner of the chip and ground in the other corner of the chip. There's not really a good way to decouple that other than really thin dielectrics. Why they did that, I don't know, but they did. So now when you have this broadband noise, where does it actually show up? It shows up every place that you have one of these resonances. So when is it important? The answer is it's always important. And it's almost always as easy to make a flat impedance power rail as it is to make a not flat impedance rail. So if you go into it understanding how it is that you make it flat, everything gets better because of it. That's true of voltage references and low noise amplifiers and op amps. All of these things are affected by that impedance peak.
So if you would like to improve the example of what you were talking about, what are the steps? What do you do? How do you know how to improve it?
So when you look at this chart, you can see that we have this big resonant peak in the red.
You still need to get the chart.
Yeah, well, that you get by measurement, right? Okay. Or by calculations. Okay. So, for example, if you look at this equation here, it's a nasty-ish equation, and they get much bigger than that. That comes from the simulator. We generally don't actually need to calculate this equation. But different regulators are going to end up with different excess inductances.
What is in this equation?
So this equation is actually the power supply modulation. This is all about the VRM, right? So one thing that I have a choice of is what VRM am I going to choose? They're not all the same. The manufacturers pretend they are, but they're not. If I choose a higher frequency VRM, it's generally going to tend to have a lower excess inductance. If I properly design it with a wide bandwidth, I can end up with much lower inductance. So the first term is the power supply, and that is this increasing edge. And we can get that either by simulation or by measurement. I have a lot of papers on modeling VRMs. And so we can get that from a model or we can get it directly from a measurement. But that's the first one.
So basically, if you don't place any decoupling capacitors, then after some time, after some frequency, it will go up because of frequency of the power supply.
Yes. In this case, at about roughly 50 kilohertz.
And is it because the switching frequencies, or what is, how it?
No, it's because of this equation, which
Mm-hmm.
does include switching frequency and also the output filter
Mm-hmm.
and slope compensation and the feedback compensation and all these things. So, we have control over it from this equation too. So part of it is for the power supply design engineer to understand how to design the VRM to get the minimum inductance and what controls it. In fact, the very first paper that I did with Heidi and Jack Carroll together was in 2018 for DesignCon. And it was because there was a Xilinx DDR demonstration board that had power supply issues. And they sent it to me and I made the measurements and I figured out how to fix it. And we did a paper about it. But a couple of things came out of it. One is that we really needed to reduce the excess inductance of the VRM, and the VRM had very little options for doing that. So we looked at this equation to figure out what we did have control over that we could use to reduce that excess inductance. And one was switching frequency. So we increased the switching frequency to get the excess inductance down.
Mm-hmm.
Of course, there's a negative side to that too. We dissipate more power at a higher frequency, the efficiency is lower.
Mm-hmm.
But we can get lower inductance because we need to fit the maximum, the amount of capacitance that it takes to damp that. And if I can make less inductance, then it needs less capacitance. That's actually the bulk capacitance for the VRM. That's how much bulk capacitance it takes.
Mm-hmm.
Once we get to the bulk capacitance, then the next stage is, well, what is the ESL of the bulk capacitors and the planes from the bulk capacitors to the ASIC? That is the next inductance that we need to damp. That's this one here.
Mm-hmm.
And so you can see that for us to tame that one, we would have to have a capacitance here that is 25 milliohms at, maybe about a megahertz or so. That would set the amount of decoupling capacitance that it takes to keep flat. And of course, we still need to observe the target impedance. So we need that amount of capacitance, but with 25 milliohms of ESR. And if the ESR gets too low, then we end up with this dip. And then we kind of play whack-a-mole. So it looks fine over here. We have very low impedance. But if we looked out beyond this chart, now you'd see this new peak that we created because of this dip.
Mm-hmm.
Right? You played this game and push it down over here and it popped up over there.
So is it basically when you always go up, you always go down, and then if you go too deep down, then you go also very high up?
Exactly. Yeah, for every action, there's an equal and opposite reaction, right? So if we push it down over here, it's going to go up somewhere else. What we want to do is we want to try to make sure that all of the energy got delivered to the ASIC and there wasn't any reflected back, because that's the resonances. So if you really had only one equation, this would be it. C is equal to O R squared. That is what governs everything about this power rail. And you can see here at a 20 picohenry excess plane inductance, and that's not much. 20 picohenry is a really tiny plane inductance. That takes 2,000 microfarads of decoupling capacitor at the package. And so if you get a 4.7 microfarad decoupling cap, maybe, and it loses capacitance because of DC bias and also because of AC bias, you'll get maybe 2.2 microfarads out of it. That's 1,000 capacitors. And also, unfortunately, those capacitors are on the bottom side of the board and the ASIC is on the top side of the board. So we do have all of these vias that carry the capacitors from the bottom to the top, and that adds inductance. So then we need a lot of capacitors so that when we put those in parallel, we end up reducing the inductance at the top side of the chip. Because we need to get it down below that 20 picohenries.
Do we need to place them some specific way, the decoupling capacitors? What is the best way to place them?
We do. And there is, there's a lot of effort that goes into what is the best way for us to place those. One of the things that Heidi Barnes really likes to show is that we can get these capacitors to mutually couple if we rotate them so that each one is in the opposite direction. Then we end up with a plus next to a minus and a minus next to a plus. And that'll tend to reduce the inductance of that pair of capacitors. A lot of people place them in a herringbone fashion. That allows us to maximize the amount of capacitance, and also we can use that to try to maximize coupling from capacitor to capacitor in order to get field cancellation in those vias.
Why does it reduce inductance when you place plus and minus capacitors this way?
Because the vias themselves actually do have inductance, right? And the inductance of the via pair of the capacitor is a function of how far apart the vias are. In an ideal world, we would get the vias inside the capacitor and not outside the capacitor, because the closer we can get them together, the lower the inductance, the better they'll couple. But then we can get the capacitors to be really close together so that this plus and this minus are really close together too. That'll minimize the inductance between this pair. And so that'll push the whole inductance down. The whole idea
it
is to try to
minimize the
minimize
inductance
that
between the vias?
Correct.
Oh.
Correct. We want to get that to be as effective as we can. And so where it is that we actually place the vias becomes a really important criteria too. The closer we can get the vias together, the plus and minus, the closer we get those together, the lower the inductance is going to be. So really, we'd like to have the two vias, right inside here, except that as the diameter gets smaller, the inductance also increases. So there is some optimal placement for the vias that'll get us the maximum inductance. And then if we can get capacitors to be really close together, then we can get this one to couple to this one. That'll also help to drive down the total inductance. There are people like Alan Martin, he's a good friend, and he used to be at National Semiconductor, but now he's an independent, and he's been doing a lot of work on how we get mutual coupling between capacitors based on their orientations.
Mm-hmm.
And there's a whole science just to that, to make these as effective as possible. And here you can see, here's the ASIC, and you can see all the bumps. And so the first question is, how many capacitors do we need in order to get to the capacitance? And then the second question is, and how do we maximize the coupling within those capacitors to minimize the inductance through the vias?
Mm-hmm. So on this picture, you are showing that the smallest size capacitors are directly under the BGA, and then you place the
Correct.
bigger capacitors a little bit away because they don't fit under the.
Correct.
But are not they like too far away? Are they still going to help?
They do. If you look at the inductance changes as we get from the VRM towards the ASIC. And so it's the highest at the bulk capacitors because we see the ESL of the bulk capacitors. So that's still pretty high. And then we go through the plane getting close to the ASIC. And so we added some plane inductance there. By placing capacitors that have much lower inductance than appears at that point, we do reduce the inductance. So yeah, using these 805s and 603s, we can reduce the inductance from the VRM and the planes getting close to the ASIC to the point that we minimize the capacitance that we need to be under the device. But I don't want to say that that means we don't need a lot of capacitors under the device. I'm saying that it's the benefit of all of these capacitors around the ASIC that got us down to the 20 picohenries that still requires 1,000 decoupling capacitors. And if we didn't have these capacitors, we would need a lot more than 1,000 decoupling caps, which wouldn't fit.
Okay, what do you have on the last picture?
This one here, this shows how it is that you might layer a board in order to try to figure out how to minimize that inductance. So here we have the decoupling capacitors on the bottom of the board. And so now we want to try to use the vias here. This is where we're minimizing the inductance from the decoupling cap up to the ASIC. So we want these vias to be as close together as we can get them. And then here you can see we want thin dielectric layers on the top. And here's the decoupling caps. Here's these over here.
Mm-hmm.
That one's over here. We want to try to minimize the inductance at that point. And so we can do that using high dielectric layer.
Oh, I
materials.
understand. So basically, if you have correct stack up, then it really doesn't matter if you have them around the chip because it can be
Correct.
even better than having them under the chip, because
Correct. In fact, if we can get, some high dielectric layers here in the top, that can help us to minimize the number of capacitors that we might need on the bottom.
Mhm.
It's about minimizing the inductance from this capacitor to the ASIC. That's it,
And
right?
basically, because the length of the via in this case is much shorter than if the decoupling capacitor is under the chip, then it can be like super useful.
Exactly. That's why we don't really love these capacitors on the bottom. It's the only place we have to put them, but they're really far from the ASIC, right? And in fact, when you look at your stack up, one of the things that you want to think about is how thick is the board at the end of the day, because the thicker this board gets, the harder it is to deal with these capacitors. The vias get longer, and longer vias means higher inductance. That's not a good thing, right? So that's all part of this thought process, is how do we minimize the inductance at the ASIC?
Okay. What slides we skipped? What is on the slide 6?
Right. And so one of the notes that I made here is that all of this requires extensive EM simulation. You can't do these power plants without EM simulation.
So how do you simulate it? Like, what do you get like model from the chip from the manufacturer, or?
A lot of the manufacturers do have S parameter models for their chips. Otherwise, you need to measure them or estimate them. But if we want to know how much inductance our power plane has, we can simulate that,
Mm-hmm.
right? We just need to keep going back and forth between exporting ODB++ files and importing them. So how this starts for most engineers is to try to figure out where it is that they can get the VRMs, and figure out what that relationship looks like. How many decoupling caps does it take based on how many layers? How much access area do I have to the chip? And these very high current power rails, typically two sides of the ASIC are given to the power rail, and two sides of the ASIC are given to the IOs, right? The
What does
power
it
guys
mean,
can't
two
have all of it.
sides?
What's that?
What does it mean, two sides?
Well, the ASIC has four sides. It's a square.
Oh, okay.
The power supply can't get all four of them. So in general, we get, half of those sides
So you
for
can
the power.
have like really big plane going up to the half of the chip, and then on the other one, on the other side.
Right.
Okay.
Of course, that helps us minimize the inductance if we can have power coming from both sides. Otherwise, the VRMs on one side would have to reach the other side of the ASIC. So the average distance between the VRMs to the center of the ASIC would go up. So typically we use both sides. Now the question is, how many layers do we need to interleave in order to get the number of capacitors that we think we could fit? And that's going to determine how many layers. And part of that is also going to be how thick is the copper, because we do need to carry the current also. And we can get these special printed circuit boards that have 10, 12, 14 ounce copper. In extreme cases, we can even get up to 60 ounce copper on an inside layer, but that's going to have a lot of skin effect. So it's generally better if we can use maybe 2 ounce copper in inner layers and then interleave them.
Mm-hmm. So basically, even if you have like very thick copper, not whole copper can be used to deliver power, because it can only, the current may flow only up to a specific depth, depends on frequency.
Exactly, because of the skin effect. The depth will be really low. So that's not really ideal.
But if you have like more layers, does it mean it's going to flow through?
It does. The skin effect will be much lower because the copper is much thinner. So it penetrates much more of the trace depth.
Okay.
And so
I would
multiple interleave layers is always going to be better than a single copper layer.
I would like to go back to the simulation. So basically, can you simulate this even without the model of the chip? You only simulate the parameters of the path between your power supply and the power pin, correct?
Yeah, sure.
So you would like
we
to
can
see
simulate the board. Yeah, we don't need the ASIC to simulate the board,
Mm-hmm.
right? What we do need to
Is the
estimate
target
is what is the
impedance.
characteristic impedance of
Mm-hmm.
the ASIC, right? So it's really helpful if we know what frequency we need to decouple the ASIC up to,
Mm-hmm.
and what is the characteristic impedance of the ASIC.
And then you make simulation of PDN impedance, and you
Exactly.
try to make it flat at the target impedance for your chip.
Right. So if we know the characteristic impedance of the package, that's our R out. That was the denominator squared. Right. And if we know the inductance, that's how many capacitors we need to fit. Or we could work backwards and say, here's how much capacitance we can fit. What do I need to keep the inductance to?
Okay.
Right. Either way you want to do that. In the DesignCon 2018 paper, we actually had to work backwards. Here's how much capacitance we could fit. And that means that I can tolerate this amount of inductance. How do I get down to that amount of inductance? And you know, it's a bidirectional equation. It works both ways. At the end of the day, square root of L over C and R have to agree with each other, or you're not going to end up with that flat impedance you needed.
I understand. Okay. So what is on the next slide?
So then we talked about the thin dielectric layers and how it is that the thin dielectric layers can minimize the inductance. And you can see that here, right? Much less inductance.
Okay. First I'm reading what is in the text.
Mm-hmm.
The high K of the material offers. What's high K?
So what is the dielectric constant? FR4 has a dielectric constant of 4. High dielectrics have a dielectric constant of maybe 24. Right? So because of that, characteristic impedance is the square root of L over C, and L is the distance between layers. So these high dielectric constant materials first have very thin layers, so it minimizes the inductance a lot. And it's also highly capacitive, right? So it minimized the impedance, it maximized capacitance. So it did 3 things really. One is it gave us really low plane inductance. The second is it gave us really low characteristic impedance. And the third thing is it gave us the capacitance that allows us to absorb the higher frequency cavity resonances. So there's a lot of benefits to using high dielectric materials close to the surface. But there's also downsides to it also. It's a brittle material, it's difficult to process, and it's expensive.
This is interesting stack up because you can very nicely see they have this power and ground plane couple very close to the top of the board. Yes. And then the rest of the power plane and ground planes are in the middle. So this is what you would like to have in some stack ups, like just have this kind of couple somewhere close to the chip.
If we can get it close to the chip, then that minimizes the inductance right through the vias. So it gives us the maximum benefit of those topside decoupling capacitors.
So at least one, you would like to have at least one couple close to the, okay.
Yeah, exactly.
Okay, what is on the next slide?
So the next slide was, we talked about the position of those. Now, we could talk about carrying the current. So a lot of people think that this is really about, you know, the copper thickness and how do you carry, you know, 800 or 1,000 amps across the board. And I don't want to minimize that. You know, it does take some significant copper. So maybe, you know, 14 or 15 ounce copper is the total that we're using to carry the current from the VRM to the chip. But that's distributed over quite a few layers. So, you know, if we do that in 6 layer pairs, then that's only 2.5 ounce copper, 2 ounce copper. That's not really a problem.
2 ounce is like standard copper.
Yeah, that's pretty standard. So, but now what about the resistance? The resistance itself isn't generally too big of a problem because the resistance we can deal with by remote sensing the VRMs, and most VRMs do have remote sensing actually on die. Right, there's generally a SPI hole that runs from the device through the package and comes out through the board, and we can use that to remote sense on the package.
How does it help if you have this remote sensing?
Well, because that eliminates the voltage drop that occurs from the resistance of the path will still dissipate the power, but we won't have the voltage drop associated with it.
Mm-hmm. So
Right?
basically, it kind of add this voltage drop back to the output or something.
Exactly. Exactly. So I don't want to say that the resistance is unimportant, but it's not the biggest one of our problems. It's one of the smaller problems. And of course, there are these high current materials that are designed for moving current around the board. And, like this Tayo Kogyo material, they can do 14-ounce foil in inner layers. And they can etch that to a 15 mil pitch, which is really interesting. They can also do 60-ounce inner copper bus bars. So just moving DC current around, they can do up to 60-ounce copper. And you can see one of the interesting things they have here is they have copper coins.
Mm-hmm.
And those are, copper slugs that go all the way through the board. And we can use those to move heat from one location on a board to another another
So it's not
location.
to carry current, but to
It's
transfer
mostly
the
to move
heat.
heat.
Mm-hmm.
Yeah, that's more to move heat. And I mean, that's another tool in our toolbox. Again, it's a more expensive material, but it's not because we can't get it. We can certainly get it. It's not the way that most of these boards are designed. These tend to be used much more for things like moving high current around, and automotive is a great application for it. And I think a lot of their customers are automotive, where they're moving a lot of high current around. And this will
But
do
for
that
lower frequencies, or
for lower frequencies.
because for the high frequencies you would not use whole thickness anyway.
Because of the skin effect. It's just not a whole lot effective for skin effect.
So is
It
this
is
used
very
like
effective at thermal.
in
though.
LED applications, or
LED is one application, yeah, for sure.
Okay.
Any place where we have a lot of heat that we need to move around, it's a great way to move heat around. The high current 48 volt power rails and electric cars, those benefit a lot from these high current layers. But that's not really our biggest issue. And we can use this, to move heat around. If we want to move heat away from the ASIC, we can use this to help do that effectively. But we can do it just as effectively with lots of thin layers, lots of 2 mil layers will do it just as well. But again, when we think about the heat, remember that there's this ASIC that's dissipating a kilowatt sitting on this board. And that kilowatt, most of the heat gets extracted to the top through the cooling system that cools to the top of the chip. And then a lot of it flows through the balls back into the board, right? It goes right through the bumps to the board. And so you got this ASIC that's got a kilowatt in it, dissipating power that flows into the board. And then you got the VRM that's pretty efficient. And maybe that's dissipating, another 50 watts, or maybe let's even say up to 100 watts that's being dissipated into the board. That 100 watts is much smaller than the 1,000 watts that's being pumped in from the ASIC. So you got heat going into the board from both directions. And it's going into the board from both directions, and it also goes out of the board from both directions. So it becomes important to manage that heat, but it's not really the heat from the VRM that's really the critical part. And I think that, one of the tools that's important because of this is that now EM simulators actually do in large part include electrothermal simulation too, like ADS, right? We can do the EM simulation, and we can also do the electrothermal simulations at the same time. And that'll tell us how heat flows in and out of the board, because it does become important to manage that.
So how does it work? You specify the thermal resistance or stuff, I don't know how it's called, and then
right. So
you
we can
apply
provide
some heat on the chip, or
yeah. So we could provide a thermal resistance from the ASIC to the board through the bumps, and then we could define what it is that the cooling system that's attached to the top side of the ASIC looks like. And then we could assign power dissipation to the VRMs. And then when we run that simulation, we'll see the heating effect from each of those devices. And we'll see how the heat flows in and out, but it'll give us the temperatures at the devices.
Okay. What is on the next slide?
So for me personally, this is one of the bigger challenges, is that these power rails are very well controlled. And very well controlled means that there's lots of different control loops. There's a control loop that manages the output voltage. There's a control loop that manages current. There's a control loop that manages the load line, right? What it is, the effective resistance of the VRM looks like. We're saying that you have to make it flat impedance. And there's two ways to make that flat. One is by design of the VRM, and the second is by management of the VRM. We can actually force the VRM to control impedance to a fixed number. And that's very often the case. In fact, you'll see this chart here. It's a little bit hard to see, but that is the 100 microhm power plant impedance, and that is controlled by a control loop. And then we have negative resistance of the VRMs that tend to become unstable with the power source in front of the VRM, the intermediate bus converter. So we have all of these control loops that are all interacting all the time.
So on these graphs, there are like different...
Each one of these is a different control loop. And all of the red charts are active ones, and all of the blue ones are ones that aren't active at the same time. And the goal in this is to figure out how to tune them, right? So if we look, we need to make sure that all of these control loops are stable under all the conditions that the power supply operates under. And that means tuning the feedback systems of all of these different sensors, the remote sense sensor, the impedance sensor, the voltage regulator, the current regulator, all of these, each one has to be assessed. And the way that we do that is using, a novel method that I actually developed called NISM, non-invasive stability margin assessment. And that uses impedance to convert impedance to stability. And so we take each one of these feedback loops and we convert it using NISM to a stability factor. And then this chart here in the bottom, that lists the stability factor for every one of the control loops.
Okay, can we go back on the previous slide? Because I still don't understand what we see on these pictures, because I can't see.
You're seeing gain and phase plots of every control loop in the power system.
So it's frequency and
frequency and magnitude and frequency and phase. These are Bode plots.
Okay. And so these are, when you say control loops, it means each control loop has some input.
Yes.
And
yes. Every one of these inputs controls the power supply.
Okay. And these are basically the inputs on these control loops.
Correct.
Characteristics on these control loops.
And so how do we make sure that those control loops don't oscillate?
Okay. So basically, for example, when you are sensing the resistance or something, then you really would like to still have it also flat or something like that?
Yes. Yeah, in fact, here you can see, here's the flat part of the impedance. And in this particular power supply, they can control that. They can set the impedance of the power rail to anything they want. It's just a programmable function. And so they tell it they want it to be 100 microhms, they want it to be 50 microhms, they want it to be 200 microhms. It's programmable. And that control loop makes it flat like that.
So what is on the first graph?
Each one of these is a different stability loop. So this one you can see is the input filter.
Okay. Input filter, it means like input capacitor, input inductance or something. That's
so there's an input filter, and I said negative resistance of a switching converter, right? The input impedance of a switching converter is negative.
And this is the impedance characteristic of this input.
Correct. And so a negative resistance tends to oscillate with a resonant network.
Okay, and you have to find all these possible problems with every single loop.
Every
you
one
don't
of
want to have there any peaks or drops.
Exactly. So we need to assess them all simultaneously because they're all functional at the same time.
So it's not only about the output impedance. You don't want to have only on output impedance these peaks, but you don't want to have them anywhere in the power supply.
Correct. And every one of these loops that's controlling some function needs to be assessed to make sure that it's stable. And the way that we do that is because, I mean, ultimately we have to actually design all of these feedback loops, right? How do we compensate them all? The way we do it is we convert each one of these loops to a number. And here you can see the numbers. So I can see a number associated with every loop simultaneously. Right? And each one of these loops has a feedback network and a frequency compensation term. And how do we tune all of those loops at the same time? Every loop we tune affects every other loop, right? They all interact together. It's kind of like playing whack-a-mole. You push it down over here and it pops up over there, right? So how do we do that? The way we do that, because I'm a lazy guy, I'm very lazy. And so I use the ADS optimizer. And I said, I'll tell you what, here's all the knobs, right? You have access to all of these controls. Set anything you want under these knobs to any position you want, but make all of these greater than 0.85. I want every stability factor to be greater than 0.85. And ADS does that in just a few minutes. And it was able to simultaneously tune all 11 control loops.
So basically you provide some kind of relationship between all these loops.
Correct.
And it will go through all the kind of possible options and come up with the one which is most stable.
Exactly. And it says, okay, I came up with a solution here. Everything is better than 0.85. This should work for you.
And then what does it mean? You need to add some resistance and capacitance inside of these loops, or?
Well, those already exist. That is the feedback compensation. And the VRM already has frequency compensation. We just don't know how to set it. And so this tells us.
So it is inside like some registers or something? Or some extra pins?
In digital power supplies, it's in registers. In analog power supplies, it's in components. Mm-hmm. But this is actually the result of equations, and the equations came from the simulation. So when this finishes, it says, okay, everything is above 0.85 now. It also provides a table and says, here's all the component values. And so then we go install all those component values into the power supply. We check it to make sure that we did meet all the stability criteria, and then we're done.
So this is basically the reason why if you have, or when you have this more complicated power supply, then very often you can see there all these additional small capacitors and resistors. That's why you need to use them, because they compensate this.
Exactly. That's what controls all of these feedback systems. And we need to control all of them. And they are all interactive, right? They're all active at the same time. And each one affects every other one. So they all become kind of nested. And so it's really important for us to understand how those relate. Now, we could try to do this with Bode plots. I mean, engineers are pretty familiar with Bode plots. And for every plot, we would have to go calculate the phase margin and the gain margin, and then the stability margin, or we could draw it on a Nyquist chart. It becomes really difficult to do.
You change one and then something will completely.
Yeah, and exactly. And it's even more difficult to try to do that in an automated fashion. So rather than do that, we used NISM to compute the stability factor of every loop. And then it was just a single number that we needed to manage. And, we always had NISM in ADS, but not everybody did. And it is actually in ADS now in beta, and it will be available in the next release. So that makes it much easier for us to tune all of these networks. That, for me, is one of the challenging jobs. Is not so much carrying the current across the board. That part's not so hard. And calculating capacitors, that's not so hard. Tuning all these control loops, that's hard.
Okay. And how do you specify the relationship between all these loops?
So we do it by measuring impedance. And so each one of these loops is an impedance measurement at some point. And then that impedance, we actually look at these peaks, the impedance versus frequency. We look at that peak, and that peak tells us about the stability margin. So the NISM technique, the actual method that I created, takes this number and converts it to this number. And then from this number, we can convert that to a phase margin or a gain margin. But in the intermediate stage, it's just this number, which is stability margin. And so we just get from each one of these curves to that number. And once we have that number, we say, okay, great, higher is better. How high is high enough? Zero point 0.6 is pretty good. 0.7 is pretty great. 0.9 is pretty optimal. 1 is perfect. So 0.85, that's pretty good numbers. I said, let's try to make it 0.85 or better. And if it didn't do that, maybe I would have had to learn to like 0.75. But it didn't. ADS had no problem reaching 0.85. Once we get through all of that, like I said, then we have to actually put it into the board. And then we need to go measure all these to see if we got them right. And there you go. You can see all the dotted blue lines. Those are our measurements. And all of the red lines are the simulations.
Nice.
Okay, so yeah, you're right. A lot of effort goes into getting to that model, but a lot rests on it, right? There's a lot of weight on getting that right.
I had no idea that actually it's so complicated to design like proper power supply.
It's a really big deal, and in a lot of these high power computers, these ASICs are $1 million chips, maybe even more. And so it's a really big deal to make sure that we get this right, because if we don't, it could end up killing $1 million chip.
$1 million chip.
$1 million for one chip. Yeah. In fact, there are chips that cost even more than that. But yeah, these can easily be $1 million a chip.
Why are they so expensive?
There's a lot of reasons. One is because they're unique. A more important one probably is because the volume is pretty low. It's not like an i9 chip where Intel is going to sell tens of millions of chips. This could be hundreds of chips, maybe 1,000 chips. But the development cost is huge, and the development cost has to be amortized over that number of chips, and the processing has to be amortized over that number of chips. And so at the end of the day, it becomes quite expensive, and that includes the cost of the design, the cost of fabricating it and testing it, and it's all amortized over a relatively low volume.
It must be like super expensive. I can't imagine like if there is a mistake on the chip or something, like
it happens.
It has to be.
It happens, and a lot more often than you think.
But I guess some part of the chip always work. Maybe some other parts may not work. I don't know exactly how they build it. I would expect they build it the way that at least some of the parts of the chip will work.
A lot of it is heritage. So a lot of these are developed incrementally.
Mm-hmm.
Right. So we take this version of the chip and then we incrementally improve it to add this, or we incrementally improve it to use a smaller geometry or something like that. Right. So that you learn along the way. But yeah, there generally are more than one iteration of the chip, and that also gets amortized into the cost. And then there's a second reason too. A lot of the work that I do is satellite work. And for a radiation hardened, high reliability FPGA, even a standard FPGA like a Vertex 7 is maybe $300,000 or $400,000 just for one chip. And so they get expensive for a number of reasons. And because of that, it becomes critical for us to know how to measure the power plane without sacrificing chips to do it. And it becomes really important that we get these power planes right.
That's what I wanted to ask. Because normally, you just go to DigiKey, you find a chip, you find a reference design, place it on your board, and it works. So what I'm thinking about, like, when you really would like to spend so much effort on going through so much work.
Yeah, when you get to 1,000 amp power planes, you don't go to DigiKey and find a nice part. It works the other way around. It's a lot more critical. I teach worst case analysis, and one of the things that I like to teach is that how much do you spend? How much effort do you put into this? It's based on the answer to a question. How important is this? What happens if you get it wrong? We all had these situations maybe a decade ago where, we had to reboot our computers and our phones once in a while because it lost touch with reality or something, right? And we just learned that you reboot stuff. That's all. We just reboot it. Oh, the TV doesn't work. I can't get to Netflix. Reboot it, and then it'll probably work, and that's fine. When
It's
you're up in
still the
space,
case. I was just doing this yesterday.
yeah, when you're up in space, you don't get the luxury of let's just reboot it. Military and defense stuff, you don't just get to reboot it. So the question is, how important is this? What happens if it doesn't work? The more important it is, the more attention you're going to pay to it.
Mhm.
Automotive does a really good job at this. Really good job.
They have to, because
Because
they produce also like many of them, and the cars, for example, they need to be super reliable. You can't just,
yeah, exactly. Two reasons. One is that if they get it wrong, people die. And people dying, that gets expensive, and they don't like to spend
And it's
money.
bad.
So let's try to not get people dying.
Yeah.
And the second thing is that, like you said, they build a lot of them. The worst word for an automotive company is recall. They don't want to hear the word recall. Recalls are also very expensive. They don't want recalls. They don't want people to die. And in our high reliability systems, our fighter pilots, our fighter planes, our satellites, same thing. The accelerator at CERN cost $17 billion to build. The space station costs $16 billion to build. Last thing you want to do is spend $16 billion and have it not work, right? It has to actually work. Yeah, so all of this effort goes into assuring that it works. That's the goal. Other applications like Wall Street, the investment markets, they're all relying on high-powered computers too. What would happen if those computers went down? GPS, we all rely on the maps in our phone, right? That's all relayed through, cloud computing and high performance computers. People get pretty annoyed if Google Maps kept going down. That wouldn't be okay, right?
But I
And
guess
so
there
it's
is some
really,
redundancy or something, which probably, I don't know.
yeah.
Yeah. Okay, that's interesting. So, but for like Arduino power supply, people don't need to worry about this.
Um, I don't know about regular power supply people. I know that I worry about stuff like this in almost every power supply. This was a big effort. Designing this particular power supply took a year, um, but a year isn't very long in the development of a supercomputer.
What do we have on the next slide? Okay, so basically on this slide, these are all the finished measurements. So
Yeah, this just shows that the
measurements and
measurements,
simulation is
the
correct.
measurements and the
Okay,
simulations matched,
perfect.
right? It says we got it right. The next question is, so what do these VRMs look like? What kind of VRMs can do this? You don't go to DigiKey to buy 1,000 amp VRM, or do you? Maybe now you do. So you can see up in the upper right, this is a new Infineon chip. They say that is the first 1,000 amp voltage regulator solution. I don't think that's true.
If someone would like to build it, they can buy it and build it, yeah?
Yeah, there you go. And you can see they have some applications for where it is they think, currents are above 1,000 amps. You can see GPU shows up a lot, right? GPUs have incredible power consumption. I don't think it's true that it's the first true 1,000 amp voltage regulator solution, because we've been building 1,000 amp boards before. But it's a single controller chip that's dedicated to management of power stages for 1,000 amp regulators. And what does that mean? If we look at a typical power application, it looks like this. You get the big ASIC in the middle, and then you can see all the phases of the VRMs around it. This is, if I remember right, this is 16 phases.
What does it mean, 16 phases? It's like
16 parallel VRMs, and they're all frequency shifted to minimize ripples. I think this is 16 of them. And one of the things that's odd about it is you'll see it's not equally balanced. We don't have 8 on each side. Ideally, we would have 8 on each side because we want to make sure that it stays symmetrical in order for us to optimize the current sharing between them.
So basically, you would have one chip, then you would have 16 outputs with same voltage,
Correct.
but each of these 16 channels is controlled a little bit differently to deliver the current or power at the specific time. So they don't do it all the time, but they do it some kind of spread.
Yes, exactly. So now if you look at this closer, you can see there's actually a power module here on the left.
Mm-hmm.
And then here's the output switching filter inductors.
Mm-hmm.
And then here's the bulk capacitors.
Mm-hmm.
And then we talked about the smaller decoupling capacitors. Those are here.
Mm-hmm.
And then tiny ones are underneath on the bottom. Now, from a placement perspective, you can see this is actually pretty far away from the chip.
Mm-hmm.
We'd really like to get much closer than that. And so how do we get much closer than that? One is we use these smart power stages. You can see this one up here in the left. That's a smart power stage. It includes the driver, the thermal management, the current sensors, any digital interface, all of that, and the half bridge controller. So this is, in essence, is a phase. And this is one of many phases, and those are all controlled by some controller, which in many applications is a microprocessor, right? Microchip makes a lot of multi-phase controllers. And so then the processor controls all of these power stages. That's the part that's over here on the left. And then we have
so
the
you need
filter.
also a microcontroller or
Yes.
microprocessor to control the power supply.
Correct. And that's what this Infineon part is that's the 16 channel microcontroller. And Microchip makes those kinds of things also. And then we got the switching inductors and the bulk caps and then the decoupling cap. So one thing we could do to make this smaller and get closer to the ASIC is to make the switching frequency higher. And when the switching frequency gets higher, this inductor gets smaller, and then the capacitors get smaller, and that allows us to move everything closer to the chip. So that's one way to do this. Another way to do this, and it's been pretty popular in the high current world, is to use the Vicor modules. And these are what they call current multipliers in a scalable technology. So this module, for example, is 48 volts input and 1 volt output. It's scaled 1 to 48. So if we put in less voltage, 34 volts or so, we'll get 0.65 or 0.7 out. And this singular module contains everything, including the output caps. Has the input capacitors, the output capacitors, all of the control stuff. But it's just a current multiplier. It takes a voltage at the input, scales it by a constant factor, in this case 48, and it scales the current by a factor of 48. And this little module, they're pretty small.
And what is the current for this?
It's like that's what that module looks like. It's a VTM module. And that can output about 160 amps, I think is the rating. So 1,000 amps, that's 6 of those.
And is it
And
okay
6 of
if
those.
it's using like these pins? Are not these pins like too much inductance?
No, because there's a lot of them in parallel. And you can also get that surface mount too. So in surface mount, it'll have lower inductance than their, J bent devices. But remember that this is the entire current transformation, including the output capacitors, right? There's hundreds of microfarads of ceramic capacitors in here. The only complaint I would have is that the ESR of those capacitors is too low, maybe. But for our very high current applications, it kind of works. In fact, if we go back to...
So does it mean if you place so many capacitors directly under the power supply or on the power supply, then you don't have to place them under the chip?
You still, well, it depends on how close you can get it to the ASIC, right? Here you can see that this is a plot, and it does actually use those modules. You can see here's the ESR of the parallel modules, and it does get lower than we want it to get, right? We don't really want it to get that low, but it does. But it's a convenient way to get the power from the board to the chip. 48 volts, that's not so hard for us to carry the current. That's only about 20 amps, right?
Mm-hmm.
And on the other side, the 160 amps, well, the cap's are already included, the inductor's are already included, so we can move the whole power stage to the right, closer to the ASIC.
How much does
And
it
so that
cost?
helps, right? And for 1,000 amps, we only need 6 of these modules. We'd probably put 8, 4 on each side.
How much does it cost?
They're expensive. I think they're roughly $45 or $50 a module.
Really?
And you need
For
8 of those.
For
So,
100 amps or something, it's
Yeah.
only. Wow.
okay, but this is just the DC transformation from the 48 volts. We still need a regulator stage, and we still need, the control loops. That's all external to this.
So you still need control loops. It means what?
All of those 11 loops are actually controlling the power stage around this.
So you need the microcontroller?
Mm-hmm.
Mm-hmm. Okay.
But, 8 of these fits nicely around an ASIC, and it makes it relatively easy for us to manage the power stage. Just that a lot of people complain that they're too expensive. They can do better, using these little smart power stages.
So basically, this module is only like transistors, inductors, and capacitors together.
Correct.
Okay. It's not like power supply itself.
No. No,
Okay.
it looks like an ideal DC transformer.
Mm-hmm.
You put in a voltage, you get 1/48 of that voltage out at 48 times the current.
Okay, what do you have on the next slide?
So one question is whether or not gallium nitride is the answer. Gallium nitride is much higher density and much higher efficiency, and EPC does some really great things.
But what does it? What is it?
So this module is the intermediate bus converter that gets from the 48 volt bus to the 12 volt bus. Because a lot of these power stages are 12 volt power stages, but there's a lot of these computer boards all running in parallel. We don't want to run that really high current at 12 volts. So we make the boards powered at 48. And then there's an intermediate bus converter that converts the 48 to 12. And that's what this module is. And this is a 1,000 watt module. You can see it's really tiny.
Wow.
It's more than 98% efficient.
So you don't need.
And the whole purpose of this is to convert the 48 volts to 12. What's that?
You don't need heatsink for this one?
You do need some heat sinking on the gallium nitride devices, these rectangles here, but there's not a whole lot of heat. It's about 99% efficient.
Gallium nitride, these are transistors, correct?
Yeah, that's this is gallium nitride, these 4 here.
But is it transistor?
It's a field effect transistor.
Okay.
So it's a gallium nitride field effect transistor, GaNFET.
Interestingly,
just as a point of reference, the MOSFET was co-invented by 2 people, Alex Liddell and his dad, back in 1970s, I think it was. So Alex invented that MOSFET, the hex FET, and he also invented this gallium nitride.
So it is kind of like MOSFET, but different technology, eh?
It uses a different material. It's gallium nitride instead of silicon.
Because it can carry higher currents, or why is it?
It's faster, has lower resistance. Alex Liddell has a lot of presentations on what's better about gallium nitride. He said that the thing that's exciting about gallium nitride is that it outperforms silicon in every single category. There isn't anything that silicon is better than gallium nitride at.
Okay, so basically, difference is it's not using silicon, but it's using different material.
Correct. And it's much faster. It has much lower resistance. It's less expensive. Everything about it is better. But I find it particularly interesting that the same guy invented both technologies. Almost, more than 40 years apart. Right, I guess probably coming on 50 years apart.
So what else you can make from this material? transistors, diodes, or?
Yeah, mostly right now it's field effect transistors.
Mm-hmm.
So it's designed to replace MOSFETs in switching power applications, but
Mm-hmm.
you'll see it's also being used for LiDAR drivers. The automotive uses this for LiDAR. Um, there's some great examples for motor drives. It does make motors much quieter.
Mm-hmm.
And also it does Class D amplifiers, audio amplifiers. It's really good for that. And it's even been used in microwave amplifiers. Believe it or not, these power switches are so fast that there are examples of multi-gigahertz RF power amplifiers made out of these power switches.
Wow.
Yeah, crazy fast. In fact, I've made a lot of measurements of EPC devices and I've published some of them. There's an article in Signal Integrity Journal called Just How Fast is GaN Fast? And we actually measured one of these devices at 139 picosecond switching time.
Wow.
Really fast.
And
That's
if
the
they are
reason it's
fast,
so good for LiDAR.
if they are fast, it means they can like deliver the power more smoothly.
Yes, and much quicker, right? So in a LiDAR, the pulse is very narrow but very big. And so the trick is to get the current up as fast as you possibly
Mm-hmm.
can, and then to get it back off again as fast as you can. It's really good at that.
Mm-hmm.
And of course, in switching power supplies, one of the dominant losses is the switching loss, right? Because while the current is going up and the voltage is going down, they're actually happening at the same time. And there's this energy that gets lost during the transition. If we can make that happen faster, we lose less energy in the transition. That's one reason that it's much more efficient and allows us to switch at much higher frequencies. But it's also much, much lower RDS on. If I remember right, it's like a factor of 16 lower. And so the RDS on is also much lower, and that also improves the efficiency. And that's the reason that these gallium nitride converters are 98 and 99% efficient.
Nice. Okay, is there something else what you would like to mention about these?
Yeah, let's talk about testing a little bit, because testing is one of the difficulties. Like I said, these chips
You may
are really
short
expensive.
circuit and
Yeah, these chips are really expensive. Like I said, $1 million chips, right? And so we don't want to find out whether or not the power bus is good enough by seeing whether or not the chip survived. Because when the chip doesn't survive, we don't really like that very much. And so all of these power buses, they all get tested. And there are different kinds of testers. This one here is made by Intel. It's called the VR test tool. And it looks huge, and it actually is pretty big. But this bottom slice here, that's actually the electronic load. And that fits inside the ASIC socket. It replaces the ASIC. And
so
all
basically,
of this stuff,
instead of the chip, you put there this.
we put this instead of the chip. And then we can use this to step the current up and down and do the dynamic switching and different profiles and all that stuff, in order to use this to test the power distribution network instead of using the ASIC. There's a couple of problems with doing that. One is that not all power distribution networks are the same. And some are much faster and much higher current than others. So this test tool doesn't actually go up to 800 or 1,000 amps, but it also isn't fast enough to emulate today's ASICs,
Mm-hmm.
which are, multi-gigahertz ASICs. And so eventually what happens is they get replaced with these little tiny dynamic control sections like I'm showing here. And it's kind of hard to understand what this is, but this is actually the size of a 1206 chip. And inside this 1206 chip, we have a 20 amp excitation for this dynamic processor. And then we put these into large arrays in this bottom slice down here.
Mm-hmm.
And then we control all of these little devices. And in doing so, we'll be able to dynamically load the power bus at gigahertz frequencies and thousands of amps. So 20 amps a piece, and we can fit almost 1,000 of those into a socket. So theoretically, we would have a peak current capability of about 20,000 amps in a 100 millimeter socket.
is not this going to have like different target impedance as the real chip?
In this case, we're not actually even trying to emulate that impedance. We're
You
just
are
providing
only
the dynamic current. So we're
kind
actually
of
measuring the
testing the
impedance.
path between power supply and the footprint, basically.
Correct. We're actually measuring the impedance of the power plane to make sure that that matches the chip.
Mhm.
So we're not actually measuring the chip at all. We removed that.
It's
But
not
we
a-
can see the impedance of the power structure.
Yeah, okay, I understand. So it's not really important that there is no real chip. You just need to be sure what is happening between power supply and the footprint is what your
Correct. We
target
need to make
was.
sure that when the chip demands current,
Yeah,
that power supply is able to respond, and it responds in the appropriate way with a flat impedance and at the right magnitude.
hmm
For lower current applications, in fact, I think Corvo published an article just recently. I think it was in Power Systems Design, maybe last month, about they had a similar application like this, but it was for their RF pulse power amplifiers. They make high powered pulsed RF amplifiers that also have very similar requirements to these high powered CPUs, except they were 65 volts. And they needed a way to do that dynamic current testing on a 65 volt power supply. So we actually made that for them in this little tiny thing that looks like a probe, and it kind of snaps into their board and does the dynamic loading. And we put a couple 100 watts into that little probe tip.
Wow.
But this gets complicated also, because to put a couple 100 watts into that probe tip, that also has to be water cooled. And so you'll see that these probes are going to start to become water cooled also, so that we can get it really close to the board that we're testing and also be able to get the heat away from it. Right? We can't make these big devices like this anymore because we can't get it close enough to the ASIC. We need to make them really small so we can get them close enough to the ASIC. But we still have the power dissipation. We still need to get the heat out of it. And so we get it really close to the ASIC by putting it inside a probe. And then we got to water cool the probe to get the heat back out.
So for
Crazy
the
stuff.
water cooling is the connector, what is there?
So this connector is actually just the interface to their board. That's a mini SMP connector.
Okay.
So this snaps onto their board. And then there's another connector that goes to the signal processor on the other side. And this doesn't have the water channels yet. So it operates at a really low duty cycle, but eventually there'll be a water channel that comes out here also. And it'll be 2 tubes. And those 2 tubes will go to the water channel.
Nice.
You probably see that from us. I don't know if you'll see it at the end of this year, but probably by next year, you'll see our water cooled probes.
Okay, what else do you have here?
So the $1 million ASICs.
Okay, we were already talking about this one. There is the last one.
Just thank you. I had fun. It's always fun talking about, the state of the art stuff. For me, it's fun.
And that's everything for this video. I would like to say thank you very much to Steve for preparing all the materials and finding time to help me to create this video. So thank you very much, Steve. And if you have any questions or any experience with designing this kind of high current power supplies, or anything you would like to say to this topic or to this video, leave your comments. I read all the comments. Yeah, I don't answer to all of them, but I read all the comments. If you like this video, don't forget press the like button. If you would like to see my future videos, don't forget to subscribe. Thank you very much for watching and see you next time. Bye.